All right, welcome back to Chemistry Notes with Mrs. Davis. We're going to continue on and we're going to talk about page number 59. We're going to extend our models of the atom and we're going to talk about the Bohr model and we're going to talk about more about electron configuration. So how are the electrons arranged in their energy levels, orbitals? Let's go on to our notes. I'm going to share that and from our current slide. There we go, and change my display settings. Okay. All right, so let me make sure I've got my pen, and I feel like changing the color to this color blue. All right, so we have our models of the atom. So we have talked about the plum pudding model, and then we have Rutherford, and who discovers our nucleus is positive, and then the electrons are outside of the nucleus, and the atom is mostly empty space. And so now we come along, and now we have Niels Bohr. So Niels Bohr is a Danish physicist, his birth and death. So we have a lot of World War II era science going on, nuclear, the race for the atomic bomb. Niels Bohr was part of that cohort. So he improved Rutherford's model by coming up with an exact placement for the electrons in the atom. And he did this with a fair amount of math. And so this is the dawn of what we call quantum theory or quantum chemistry. So the ideas that he proposed is that each atom has 7 fixed paths that the electrons travel around the nucleus called energy levels. Please remember, this is not our final model. This is now the Bohr model, because now we're, in the 1930s, 1940s, somewhere in that time frame. And the model still is going to keep evolving. So now we have 7 fixed paths, and we call those energy levels. And so those energy levels are basically like a force field. They're not physical structures. So then around the nucleus of the atom, we have levels that build up from 1 through 7 outwards. And so each electron needs a definite amount of energy in order to occupy an energy level, right? Their atoms are held together, right, by forces of attraction, the positive nucleus attracting those negative electrons. And there's a specific amount of energy in order to then fill. And so basically the electrons are lazy. They want to fill up closest to the nucleus first, and then they're allowed to expand outwards. And so closest to the nucleus is going to have the least amount of energy. So the energy levels closest to the nucleus require the least energy from an electron, right? The electrons, want to go in the easiest way possible. So they're going to fill up close to the nucleus first, and then they're going to go outwards. So while electrons in the energy levels farther away from the nucleus need more. So then that basically means that electrons want to be at the lowest energy level possible. So less energy needed means a higher stability. So I'm going to just basically say that level 1 has less energy than, say, level 3. So the lowest energy is level 1 and the highest energy is level 7. There's 7 levels, 7 energy levels, and that corresponds to the 7 rows of our periodic table. So now let's talk about electrons. So what electrons can do, right? We have electricity and electron also start with the same prefix because they're connected to each other. Electrons can absorb energy. They're able to jump to a higher level, right? You give it a little bit of jolt of energy and those electrons can go up to a higher level. And this is a temporary state. The electron quickly has to return back down to its lower energy state, right? Because nature is going to favor that low energy state. So then it's only temporary. So what goes up must come down, right? We have to still follow the laws of the universe, right? So we absorb energy to go up, and we're going to call that excited state. And when we go back down, we're going to call that back down to what we call the ground state. And so we'll get a little bit more into that in just a bit. So now how are these electrons placed in these energy levels? So the maximum electron placement in each energy level is equal to 2n squared, where n is equal to the energy level. right? So we have energy levels 1 through 7. Remember, electrons, are likely to be found in the region called an orbital, which is within inside the energy levels. So now let's figure out how many electrons can each level hold, because this is important for you to know. So you're either going to memorize 2n squared, or you're going to memorize the numbers. It's kind of like a locker combination. All right, so first energy level, if it's n is equal to 1, so 1 squared times 2 is 2. So the first energy level can only hold 2 electrons, 2 itty bitty ones. So if I have more than 2 electrons, right, which means anything larger than atomic number 2, right? So if I even go to atomic number 3, which is lithium, that first energy level is full with 2. So the third one has to go up another level. So you fill in from the bottom to the top, right? So logical order, right? Closest to the nucleus, and then you fill in as you go. But you got to follow the rules as the maximum number in each energy level, which is 2n squared. So our second energy level, 2n squared, right? 2 times 2 is 4, times 2 is 8. So the maximum number of electrons in the second energy level is 8. So level 2 can only hold 8 electrons. If I have more than 8 to fill in that level, I got to go up to the next level, which is level 3. So right now, I can hold 10 total electrons in levels 1 and 2. And notice that this is 10 electrons is going to be neon. So that means I end the row, and now I got to go, right? So I'm going to end here at 10. And, oops, and now I've got to go down to sodium, which has 11 electrons to go. So if you notice, sodium's electron configuration is 281. So that means that it has 2 electrons in the first level, 8 in the second level, 1 in the third level. So how does that go, right? Here's those first 10. Now I got to add the third energy level. So 3 times 3 is 9, times 2 is 18. So now I have 2, 8, 18. The maximum number of electrons, right? 18 total electrons is going to end up being argon at the end of the row. All right, so then level 4 is going to hold 32. I've never seen a Regents exam ask anything above 32. So you either memorize 2, 8, 18, 32, or you memorize 2n squared. Your choice. 2n squared is a little bit easier to memorize, but you got to remember to do the math. And what does n mean? N means the number of energy levels 1 through 7. So then we have energy level 5 can hold 50. And energy level 6 can hold 72 electrons, right? So then that is all the maximum number of electrons that can be held in any energy level. So now we're going on to page number 60. Oops. All right, so I forgot number 7, which is 98. All right, so now we're going to talk about a Bohr diagram. So now this is a way that we're going to illustrate or draw electrons and their energy levels. Remember, this is just a 2D representation of what really exists in 3 dimensions, and the model has its limitations. It is not to be taken literally. So our Bohr model is this planetary model. And so we have our nucleus at the center, and that their nucleus is positive, right? Our nucleus is still positive, and the nuclear charge is still the number of positives in the center. And now I'm using these half circles, or you might see them as circles, to describe energy levels. So here's some energy levels. It's a little easier to draw these little half circles than it is to draw those little circles. And now our electrons are going to go in those energy levels. So our first energy level can only hold 2 electrons. Then our second energy level can hold 8 total electrons. So let's do some examples. All right, so let's talk about hydrogen. Hydrogen on the periodic table is up here, has an atomic number 1, so it has 1 proton. That means it has 1 electron to balance its charge. So here's my nucleus, the protons and neutrons. How do I know that those neutrons were 0? Because hydrogen has a mass of 1, and so 1 minus 1 is equal to 0 for the neutrons. Remember, if I see this little dash, this means the mass number. So here I have energy levels. If I look at the electron configuration under hydrogen, it just has a 1 underneath it, because it only has 1 electron and 1 energy level. So that 1 electron is in the first energy level. That Bohr diagram is complete. hydrogen is the simplest of the elements. So now let's go on to our next element. I have 3 protons and 4 neutrons. So this is lithium because lithium has 3 protons. And now 4 plus 3 is equal to, this is 7. So this is lithium 7. And it has 3 protons and it has 3 electrons. So underneath lithium on the periodic table, it says 2-1. That means that there's my nucleus. In my first energy level, I can only hold 2 electrons. So the first out of the 3 electrons I need to place, 2 go into level 1. The next one goes into level 2, which can hold 8, but I only have 1, so it's just got that one little bitty one in there. Now let's go on to our next one. I have 13 protons, so then that's going to be atomic number 13. So that's going to be aluminum. And then this is aluminum with a mass of 27, right? Because 13 plus 14 is aluminum 27. The atomic number is 13, so that means I have 13 electrons to place. If I go to the periodic table, where are you, aluminum? It says 283 on the periodic table, so 283. That means in level 1, there's 2 electrons of the 13. Then I have 8, right? There's 10. And now I'm going to add the last 3 to the last level, which is going to be 3. So there's my nucleus. Energy level 1 holds 2 electrons. I still have 11 to go. So now I'm going to put the next one here. The next energy level can only hold 8. So there's going to be those 8 electrons. And then the last is going to be those 3 electrons. So now that's going to be where our 13 electrons are going to live. So whatever this last level is called the valence shell. So our valence shell is equal to the last energy level. That's the valence shell. So then if that's the valence shell, the valence electrons are the electrons in the last shell, or energy level. We use those terms interchangeably, shell and energy level. So then this hydrogen 1 has 1 valence electron. This also has 1 valence electron because it only has 1. This one has 3 valence electrons. And those valence electrons are going to come in handy. They're going to be very important when we start talking about the periodic table and how elements combine to make compounds, because they do that with those valence electrons only. So now we're going to talk about our electron wave mechanical model. So now this is our last current thinking. This is what we call the modern model. And our modern model now expands on this Bohr model, because Bohr's model and his mathematical calculations really only worked well for hydrogen. Once we got into larger atoms with more complicated configurations, it didn't quite work out. It was still a useful model, and we still use it to draw how we like things to be drawn in 2D. But now we have what's called the modern or the wave mechanical electron cloud model. And this determines how likely it is to find the electron in various locations. And we say that it's the most probable location of an electron is the orbital. So an orbital is like a more specific location inside the energy level. So the Bohr just talks about things in terms of energy level. But within those energy levels, there are more specific locations, and the electrons kind of move around cloud-like. So they're constantly in motion, and it's not a predictable motion. And Austrian physicist Erwin Schrödinger is the one who's kind of come up with this model, and this is really based on, this is a mathematical model, and this is based on calculus, and this is considered still quantum theory. So this is quantum chemistry. And so here we still have our nucleus in the center, which is dense and it is positively charged. We have our protons and our neutrons in the nucleus. So now instead of the planetary model, which is with Bohr, and we talking about shells and energy levels, now we're talking about that we're going to get more specific, and then the most probable location of electrons is like an orbital, and all of them overlap each other to make like a big cloud around the atom. And then they're constantly in motion. And so now our most probable location, so then is the orbital, and it's not in orbit. So they are not in orbit and not planet, not like a planet. So not planet-like. It's more swarming cloud-like, right? Clouds don't follow a predictable path. I mean, well, somewhat predictable, but they're not, you know, like a planet. And so then that is our electron wave mechanical model. And that's going to wrap up. And we'll practice more Bohr diagrams. We're going to talk more about the excited state and ground state in our next set of lessons. Thank you for sharing your time with me. I'm going to stop my share and end my meeting. Bye.